Let's learn some IPv6 basics. First of all, binary conversion. Here's an IPv4 address, 32 bits, converted into binary here, and then the subnet mask converted into binary here. /24 and then 24 ones and 8 zeros, and then the octets here, the 192 octet, 8 bits here, and so we have 4 octets. Now, in contrast, an IPv6 address is 128 bits, and the characters are hexadecimal characters. So each character is 4 bits, and we call these hextets. So you have 4 characters in a hextet, another hextet, so there's 8 hextets, 128 bits. And here's what it looks like if you convert it to binary, and I've put a dash here to identify each character. So this is the 2 right here, and then the 0 here, and the 0, and then the 1. So just this right here is the first hextet. All right, let's look at the next slide. IPv6, 128-bit address, colon-separated hexadecimal notation, 8 hextets. On every interface, you need a link local address on each interface. Now, the link local address is locally significant only. It's not routable to another network. It's not routable on the internets. You can only use it or communicate to it on the local link, which means the local network. You can have multiple routable addresses on each interface. So each interface can have multiple routable IPv6 addresses, and there's different types. There's a global unicast address. Now this is a unicast address that you could put on your interface, on your router, or on your PC, and it's routable on the internet. It's basically the equivalent of a public IPv4 address. Global unicast address would be like a public, routable IPv6 address. Now, a unique local address is also unicast. It's for a host, just like a global unicast. A unique local is for a host. However, it's a private address. So it's similar to an IPv4 private address. Now, we don't actually really need these in IPv6 because IPv6 address space is so huge that every device in the world, if they had an IPv6 address, we could have all public addresses easily. 10 times over, 100 times over, all the devices in the world could have a unique public IPv6 address. However, since a lot of network admins are used to having private addresses that are only routable on a private network, they came up with unique local addresses that are private. Okay, there's anycast addresses. An anycast address is the same as a unicast address, but you can assign the anycast address to multiple devices. In other words, you could have 3 routers with the same address, and then it would be an anycast address. You could configure it as an anycast address, and then if you want to reach the router, you would reach the nearest device, basically the first device to respond, and that's anycast. So same address on multiple devices, and then the nearest one responds. In IPv6, we don't have any broadcast addresses. No broadcast addresses, only multicast addresses. Multicast addresses are similar to broadcasts in a way because they get sent out to multiple devices on a network. So we use multicast addresses instead of broadcast. Then each IPv6 address will have a /network prefix. It's in a /decimal notation. So when you see /64, this 64 is actually in decimal. It means that there's 64 ones in the network prefix. There are no subnet masks in IPv6. We don't use subnet masks in the same way like we do in IPv4. There's no ANDing of the IP address with a subnet mask to find the network. In IPv6, the /64 here lets you know that the network prefix is 64 bits long, and that defines the network. So here is a global unicast address example. I just made this up, by the way. So you have here /64. That means this is the 2001 2EB8 ADC1 54ED network, and then this is the interface ID, or basically like the host address. Then a link local address. This is locally significant only. Every interface would need to be routable on a network. a routable address, like a global unicast address or a unique local address, and then a link local address, which is only for the local link or local LAN. And those start with FE80, and you can see it here. And the /10 defines it that link local is defined by the first 10 bits, which is the F, the E, and then a portion of this 8. All right, let's look at the next slide. So the network prefix. The network prefix separates the network portion from the interface ID. The network prefix refers to the number of bits in the network portion. I've already stated that. So here we have a global unicast address. You see the /64. That means the first 64 bits, or the first 4 hextets, is the network. And then the last 4 hextets is the interface ID, similar to like the host address. It identifies the interface. And then here we have a /96. In this case, the network would be defined by 96 bits, and then the remaining bits would identify the interface ID. And then let's say you had a /128 network prefix. Well, that means that the whole thing is a network of 1, essentially. Kind of like a /32 identifies a single host, or a network of 1. On to the next slide. So let's break down an IPv6 global unicast address. The network portion of the global unicast address is hierarchically structured. So if we look at those first 64 bits, the first 3 bits is the IANA global prefix. So all of the globally routable addresses currently that we're using in IPv6 is just a small portion of what's the total address available space. So the first 3 bits identifies the IANA addresses that have been assigned to be used on the internet. Then the next bits, the next 20 bits up to bit 23, is the regional registry. So these numbers here would identify your regional registry, whether it's North America, South America, Africa, Asia, etc. Then the next bits here, the next 9 bits here, would be your service provider prefix. So this would be assigned to your internet service provider. And then your internet service provider will assign you your site prefix, which is between bit 32 and bit 48. This is your site prefix. So this would be your company or your organization. If you purchased an IPv6 address from your service provider, this would be your static IP address or IPv6 address of your organization. Then the last hextet in the network prefix is the subnet hextet, and then you can assign this. So effectively, you would be, okay, this is my company. This uniquely identifies my company, the 2233 here, and then I can put my own subnet using these 4 hexadecimal characters. I can assign my own subnet. Then you have the last 64 bits, which is the interface ID identifying the host or the interface on the network. Let's talk about IPv6 address compression. Let's face it, the IPv6 address is super long. It's super long, right? 32 characters is a lot of characters. So address compression is allowed. In other words, we can write this address, this is the complete address, we can compress it down to this address. Now, how do we compress and decompress an IPv6 address? It's not hard. What you do is, here's a couple of rules. Leading zeros can be omitted. So here we go, we have 0EB8, so this leading 0 can be omitted, so instead you could just have EB8, all right? And then you have 00C1 here. So these leading zeros, these 2 leading zeros can be omitted, so you just have C1. And then notice over here in the subnet prefix portion, the subnet portion, we have 0001, so that could be reduced down to just 1. We could omit these 3 leading zeros. Then the next rule is that a single instance of continuous zeros can be replaced with a double colon. So notice we have these continuous zeros here. We have 8 and then 9 continuous zeros here. So you could take this whole block of zeros here and change it to just a double colon, and this identifies a range of zeros, a range of continuous zeros. Now, if you follow these rules, you could successfully decompress this address back to the full address length here. But anyway, this is a compressed IPv6 address. When decompressing, remember there are supposed to be 8 hextets of 4 hexadecimal characters each. That will help you to decompress this address, is that you know there needs to be 8 hextets. So we know that, well, if this is easy, this is 0EB8, and we know this is 00C1, and then we know this is 0001. Well, that means we have 1, 2, 3, 4, 5 hextets. That means we need 3 more hextets. So we've got 2 hextets of zeros, and then we need to add a 0 before that 3, and we've got our 3 hextets remaining. So that's basically one of the things you need to remember when decompressing, is that there's supposed to be 8 hextets total in the address. That'll help you. Okay, let's talk about another interesting feature of IPv6, and that's SLAAC, Stateless Address Autoconfiguration. With IPv6, essentially, a host that uses IPv6 on a network doesn't need a DHCP server to get an address on the network. And I'll return to that later, because it turns out actually they do kind of, but for the most part they don't. So in other words, if you have a host, a PC here on the network, it can basically statelessly auto-configure its IPv6 address. So how's that done? Well, the PC sends a router solicitation, which is actually an ICMP version 6 message. It basically says, hey, where's the router on the network? Now the router is also advertising, and the router is saying, hey, I'm over here. So the router responds to the PC. When the PC gets the response from the router can auto-configure the address using EUI64 extended unique identifier. And basically what that is it's basically converting your 48-bit MAC address into a 64-bit interface ID. Or the PC could randomly configure the interface ID portion. So this is the auto-configure part, where the PC auto-configures the 64-bit interface ID. It can be done using EUI64, basically using the MAC address, or it could be random and randomly configure it. Then, once the PC has given itself auto-configured its IPv6 address, and it's learned about the network portion and the gateway and the network prefix from the router, it sends out a neighbor solicitation message, also known as duplicate address detection, to basically ping itself and make sure that there's no other device on the network with that address, since the PC auto-configured the address. There is a slight chance that there might be another device out there on the network that has the same address, so it sends out a ping just to make sure that no response comes back. Let's take a closer look at this. IPv6 SLAAC. So RFC 4861 neighbor discovery, SLAAC ICMP version 6. I said it uses ICMP to do this. Let's take a look at it. Step 1, you've got the router solicitation message. Now in the source address field, it's going to be an unspecified address because your PC doesn't have an address yet. So it'll be :/128. I don't have an address. The destination address will be the all routers multicast address, which is FF02, which identifies it as a multicast ::2. So this will go out, this multicast will go out, and routers will pick it up. This is a type 133 packet. Okay, then here comes the response. Step 2, the router advertisement. Now the router advertisement is sent periodically on the network, but it can also be sent in response to that router solicitation message. So in the source address field, the router will have its link local address. This is how you'll learn where the router is, where the gateway is. This is where you learn the gateway. And then you'll put that into your gateway address. And the destination address for the router advertisement is the all nodes multicast address, FF02::1. So this will go out to all devices on the network, essentially advertising that we have an IPv6 router. It's a type 134 in the type field. Okay, so then type 133 in the message and type 134 in the message. Okay, now what is in this router response? In this router response is the IPv6 prefix, which could be either one or more prefixes if there's multiple networks. However, in this case, what will the PC learn from the router? The PC learns that it's the 2000/1234 ABCD EF22 network. Notice it learns that the network portion of the address. It also learns the /64 prefix, the network prefix. However, it doesn't learn the IPv6 interface ID because it's going to auto-configure that. It also learns the router lifetime information, how long this information is valid. There's going to be some flag information in here, and the flag information is either going to be nothing, or it's going to be M for managed, or O for other. Now this is the part that helps you get your DNS server. So the one thing that the router doesn't tell you is where the DNS server is. So you're either going to have to statically configure a DNS server on your host, or if there's a DHCP version 6 server on the network that's serving just the DNS server information, then the router will set the O flag, letting the PC know to go find the DNS server information from the DHCP version 6 server on the network. That's the O. There's other information, namely DNS server, and it's out there on a DHCP version 6 server. Go find it. If there's an M flag, it means ignore the network prefix, ignore this router except for the gateway address, and go get a leased IPv6 address from a DHCP version 6 server that's going to lease you an address. The other thing that, once again, I mentioned is you learn the gateway, the source address of the router, the FE80 link local address. You learn that from the reply from the router advertisement. So we have that listed here too. So that is basically how you get most of the information off the network, minus the DNS server, which you're going to need to get from a DHCP version 6 server or statically configured. Now, let's talk about EUI64. IPv6 SLAAC EUI64 extended unique identifier. So this is when you convert your 48-bit MAC address into a 64-bit host interface ID. So notice 48-bit MAC address into 64-bit host ID. So here it is. There's my MAC address, 48 bits hexadecimal, and here's my interface ID. The result is a 64-bit hexadecimal interface ID. So what happens? Well, it's pretty simple. The MAC address gets split into two pieces, and FF:FE is inserted in the middle. So notice we've got FFFE in the middle now. Then on this address, the 7th bit from the left, so if you have 08 here in your MAC address, so 08, if we convert the 08 to binary, so we have 4 bits, that's the 0, here's another 4 bits, that's the 8, the 7th bit, so 1, 2, 3, 4, 5, 6, that's this yellow one right here, gets flipped. So it'll flip from a 0 to a 1, and what that does is it changes 08 to 0A, because we flip that bit right here, which is in the 2's place, and so now we have 2 more, so 8 plus 2 more is an A. So you have 0A instead of 08. So that's it. FFFE is inserted in the middle of your MAC address, and the 7th bit is flipped. And that's it. All right, next slide. The other piece of ICMP version 6 for IPv6 that is used on the network is neighbor discovery. So let's take a look at that. RFC 4861 neighbor discovery. So the neighbor solicitation. So the neighbor solicitation message is similar to ARP in IPv6. It also can be used to check for host availability, and it's used to check for duplicate address detection. After you auto-configure your address, you need to ping your address to make sure there's no other address on the network. So let's look at it. In the source address, you're going to have your link local address or an unspecified address if duplicate address detection. So if it's duplicate address detection, you'll have unspecified. If it's neighbor solicitation, similar to ARP, you're trying to find a host on the network. You're basically trying to resolve the MAC address of the host on the network. Then it'll have your link local address in here. Then the destination address is the all solicited nodes multicast. Now this is interesting because this is actually an improvement on ARP's function. So the destination address will be FF02, which is multicast, and then : 1 : FF, and then the last 28 bits of the destination host's IPv6 link local address. So in other words, this multicast is multicast essentially to the device that it needs to go to. So in other words, this is, you already have to know the device's link local address for this neighbor solicitation. What you're trying to resolve is the MAC address. So the switch, if the switch has been configured to be able to do this, it can actually forward this message directly to the device on the network. So in other words, instead of like an ARP which gets broadcasted and broadcasted to the whole LAN, this all solicited nodes multicast essentially is multicast to one device only. So it's a multicast that will get picked up only by one device. And essentially, it can also be sent to one device if a switch has been configured properly or has the ability to do that. So then what about, so that's the neighbor solicitation. It's an all solicited nodes multicast. And then the neighbor advertisement, the response to the neighbor solicitation, and it's used to announce a link layer address change. So if you were to change your link layer address, you would send out a neighbor advertisement, say, hey, I changed my link layer address. So your link local address is in the source. The destination is the link layer address or the all nodes multicast if you're using to announce a link layer change. Then there's some flags. The R flag, router flag, neighbor unreachable. S, solicited flag, response to a neighbor solicitation. Or the O flag, an override flag, where you're updating your address. So in the flag here, if it's an update of an address, it will be an O. If it's a response to a neighbor solicitation and it's a neighbor advertisement, that'll be an S. And then if it's a neighbor unreachable router flag, it will have an R. And this is the type in the message field. All right, this is a useful slide for you for learning IPv6 address types. A global unicast address that's routable on the internet will generally have the prefix 2000. There'll be a 2 here, or typically 2001, or a number like that. So typically it's 2000 if it's a global unicast. If it's link local, it starts with FE80. If it's a multicast, it starts with FF. If it's a unique local, routable on a LAN, private address, it's an IPv6 private address, it'll start with FC or typically FD. Modified EUI64, converting the 48 MAC address to 64-bit host ID, the 7th bit is flipped and FFFE is inserted in the middle. Autoconfiguration, SLAAC, uses router solicitation, router advertisements, neighbor solicitation, neighbor advertisements, and it uses ICMP version 6. This is how it's done. An anycast address is a shared address used to send to the nearest available device interface. It's syntactically identical to a unicast address. So the address for an anycast address could be the same as your unicast address, or, and this is curious, if you have the address with all zeros in the interface ID portion, so you have the network prefix and then all zeros, to me that reminds me of a network address in IPv4, this actually can be used as an anycast address with all zeros in the ID portion. All right, moving on. Specific IPv6 addresses that you'll want to know. So ::/0 is the all networks address used for the default route. So ::/0 is similar to a quad 0 route in IPv4. In other words, 0.0.0.0 space subnet mask 0.0.0.0. This is similar to that. It's all zeros in the address and all zeros in the network prefix. It's used for default route. ::1/128. ::1 is your loopback address. You can ping yourself, open up your command prompt and ping ::1 and you'll get a reply. You're pinging yourself in IPv6. You're essentially pinging your link local address. An unspecified address means I don't have an address yet is ::/128. Your link local address starts with FE80, ::/10 on the prefix. FF02::1 is all nodes. FF02::2 is all routers multicast. and then ff02::1:ff, and then you have 28 bits, or 6 hex characters of the address. That's the all solicited nodes multicast. It's used in auto configuration and neighbor discovery. It's similar to ARP. The process is you need to discover, this is used when you need to discover the MAC address of a neighbor. All right, configuring the IPv6 address on the router. It's really simple. First of all, you'll go into global config mode. You'll put in IPv6 unicast-routing. This will turn on IPv6 routing on the router. You need this IPv6 unicast routing to enable the router to start doing router advertisements. To respond to router solicitations and issue router advertisements, things like that, you need that IPv6 unicast-routing. Then to configure an address, here we go, IPv6 address on the interface, and then the address /64. So that's like statically configuring an IPv6 address on the network. Then this one, IPv6 address, the network portion, then : all 0/64, and then you put in space EUI64, and then the router will create a unique identifier based on the MAC address and put that in here automatically. IPv6 address FE80::1. This is basically configuring space link-local, the link local address on your router. Remember, you need 2 addresses. One that's, let's say, routable, like this one, and then you would need the link local one here. So you could use either this or this, but you're going to need this, a link local address. And in this case, it's statically configured. So let's say I'm router R1. I said FE80::1, just host 1. Over here, another way to do it is you could say IPv6 enable IPv6 addressing on the interface, and then IPv6 address autoconfig will auto-configure your link local address, basically using EUI64 for the interface ID portion. So you'll end up with FE80, and then you'll have : and then 4 hextets worth of a 64-bit interface ID configured from your MAC address. To get rid of an IPv6 address, this is a tricky one. With IPv4, you could just say no IP address, right? We used to be able to say just no IP address to get rid of an address on an interface, but with IPv6, since you can have multiple addresses on the interface, you need to type the whole thing to get rid of the address. No, and then the complete address to get rid of it, and then no, and then this will get rid of the link local. But it's a little bit longer because you have to type in the whole address.